So last time we have discussed the half-wave rectifier, which converts an AC waveform or an AC signal into a pulsating DC signal. Pero ang nangyari is kalahati lang nung waveform or kalahati lang cycle ang na-utilize. We use the ideal diode model. But this time, we will use what we call the practical diode model. That's why before we continue with the discussions of half-wave rectifier, i-discuss ko muna yung practical diode model. So last time we have discussed the ideal diode model, di ba? Ang ideal diode model, the ideal diode model, kung ipa-plot natin yung kanyang characteristic curve, so we have ID, yung ating y-axis, and then we have VD or V sub D, yung ating x-axis. So ang kuryente natin sa diode ay nakadepende sa voltahe dun sa ating diode. Kung ideal siya, 0 pa lang, no? Nagko-conduct na siya. And pagdating ng negative na voltage natin, hindi siya magko-conduct. That's why ang this represents your ideal diode characteristic curve. And yung practical diode characteristic curve natin ay susundan pa niya yung threshold voltage. For example, is silicon. So around 0.7, magsisimula na siya mag-conduct. Okay, so this is your practical diode model. Sa practical diode model, meron tayong dalawang klase. So this is the practical diode model. Medyo makapal yung sulat. Sandali. Practical diode model. Okay. Ang unang-una natin dyan is yung tinatawag na piecewise linear. Piecewise linear. So pag sinabi natin piecewise linear, we are taking into consideration the dynamic resistance or the dynamic impedance, no, of our diode. Last time we have discussed na ang diode, posible siya magkaroon ng iba-ibang value ng impedance or ng resistance. Depende doon sa ina-apply natin na signal sa kanya or voltahe. So meron tayong DC resistance and meron din tayong dynamic or AC resistance. Or meron din tayong average AC resistance. So the piecewise linear model takes into consideration this particular impedance level. So ang kanyang magiging characteristic curve, so let's say it's silicon. So this is 0.7. Ganito yung magiging itsura niya. Okay, when it reaches around 0.7, yan. So medyo ano siya, slope. Parang meron siyang slope, no? So this is how it looks like yung ating piecewise linear model. Ang kanyang equivalent circuit is ganito. So we have, for example, the ideal diode. So this is your we have the ideal diode. Yan. And then we have a series resistance, an average resistance. And then we have what we call the threshold voltage, VTH. Okay. This is the equivalent piecewise linear circuit. Piecewise linear circuit. So, ang ibig sabihin lang naman ito, equivalent circuit lang siya. Hindi common nakalagay dyan. Maglalagay na tayo ng power supply, maglalagay na tayo ng resistor, maglalagay na tayo ng diode. This is just an equivalent circuit. This is how it behaves. So, ibig sabihin, it takes into consideration the average resistance, kaya meron tayong slope. Okay, unlike yung ating ideal diode model, it doesn't take into consideration the average resistance, kaya diretso lang siya. This part, kinonsider niya kaya merong slope. Okay? And then, it must overcome the barrier potential. The barrier potential being our threshold voltage. So this is the equivalent circuit for the piecewise linear circuit for the diode. Yung pangalawa, yung sinasabi ko sa inyo na practical diode model is what we call the simplified equivalent circuit. So we have the simplified equivalent circuit. So ang kanyang characteristic curve, ganito yung magiging itsura. So pagdating ng 0.7, let's say silicon siya, it will increase ang kanyang kuryente. Kunwari na lang diretsyong-diretsyong Y kasi tumudulas yung kamay ko dito sa writing pad ko. So ito yung characteristic curve ng simplified equivalent circuit. Again, it doesn't take into consideration the resistance level, kagaya ng ideal diode. Ang nagte-take into consideration lang ng resistance level is yung piecewise linear model. So these are different ways how we can express, how can we represent yung ating diode. Okay? But most of the time, we will use the simplified equivalent circuit. So ito ang kanyang equivalent circuit. No? Meron tayo ditong threshold voltage and then meron tayong ideal diode. So this is the equivalent, the simplified equivalent circuit. Okay? So ibig sabihin lang nito, kailangan niyang ma-overcome yung threshold voltage na yon at kailangan positive ang anode with respect to the cathode. Di ba yun yung dalawang criteria na sinasabi ko sa inyo? In order for us to consider na naka-forward bias yung ating diode. So that is your simplified equivalent circuit. While itong ating green na to, this is another practical diode model, but this is the actual. Ito yung actual. This is derived from Shockley's equation, yung dinerive natin last time. Okay? So we have utilized last time ito, yung ideal diode model. Ang ideal diode model, positive ang anode, negative ang cathode, matic forward bias, kahit hindi maabot yung 0.7. Ang practical diode, simplified equivalent circuit, positive ang anode, negative ang cathode, but it should reach 0.7, 0.3, 1.2, or any value of the threshold voltages indicated sa mga diodes natin. Okay? So we will use the simplified equivalent circuit sa ating next analysis ng half-wave rectifier. So let us recap dun sa half-wave rectifier na baka nakalimutan natin. I'll just draw the input versus the output. Tumatabingi yung ano ko, teka. Yan. So this is the, let's say this is the input voltage versus time. So meron kang sine wave. This is the positive half cycle and this is the negative half cycle. Pagdating naman dito sa output natin, anong magiging itsura niya kung half-wave rectified signal siya? So let's say positive half cycle, ganito. Pagdating ng negative half cycle, mafa-flat na siya. Pagdating ng next positive half cycle, may sine wave ulit, and then wala. So in this way, kalahati lang nung cycle natin ang na-utilize, which is very wasteful. So nasasayang yung ating negative half cycle. So mamaya i-calculate natin yung what amount of DC is being taken from the half-wave rectified signal. Ano ba yung nakukuha nating DC? Kasi objective nga ng rectifier, transform AC to DC. But the question is, how much DC are we getting out of it? No? So mamaya mag-i-integral tayo ng compare. Okay. So let's say the peak voltage is 10 volts. Ang magiging peak voltage din nito sa output mo is roughly around 10 volts. This is for ideal. Okay, that is for ideal. But in terms of the practical simplified equivalent circuit, ganito yung mangyari. So let's start off with the positive half cycle. So i-drawing ulit natin yung half-wave rectifier. Sabi ko sa inyo, half-wave rectifier, ilang diode ang meron? Isa lang. So let's say it's pointing to the right. Okay. So this is your resistive load. And let's say this is silicon. Kasi yung nauna nating discussion before, ideal yon. So this is now silicon. So ang input natin, let's say 10 volts peak. Okay, yung pinakamataas ay 10 volts peak. Sa positive half cycle muna tayo. So positive yung taas, negative yung baba, and we will determine the output voltage V sub O. So ang V sub O natin dito is hindi magbabago yung kanyang orientation. So yung positive ang nasa taas at negative yung nasa baba natin kasi it is a measured voltage. So finix lang natin na ganyan. Okay, pinakita ko pa sa inyo last time yung oscilloscope probe natin, di ba? So, for example, I have here the oscilloscope probe, nandito yung positive, nandito yung negative. Makikita natin yung output sa oscilloscope. So, sa pag-analyze natin using an ideal diode, matic itong matic siya naka-forward bias kasi sa positive half cycle, positive yung anode, negative yung cathode. Pero sa silicon, hindi agad-agad. Dito mapapansin natin, positive ang anode at negative yung cathode. Pero yung ating voltahe will range from 0 up to 10 volts, then from 10 volts down to 0. So nagbabago bago yung voltahe natin. Okay? So let's start off with 0. So I will make here a table. I'll make a table here. Let's say the input here is, let's say 0 muna tayo. So condition of the diode. Okay. So positive half cycle. Okay. Kapag 0 ang input natin, hindi pa agad siya naka-forward bias. Bakit? Kasi kailangan niyang maabot ang threshold voltage na 0.7 volts. 0 pa lang input natin. Okay? What is the condition? It's still considered to be reverse bias. So I'll write RB for reverse bias. Mag-increase tayo ng 0.1. May 0.1 na. So let's say 0.1 volts. Is it enough para i-forward bias yung ating silicon diode? Not yet. So anong condition ng diode natin? Reverse bias pa rin. So 0.2. Reverse bias pa rin kasi aabutin nga niya yung 0.7, di ba? So on and so forth. Let's say inabot niya yung 0.7 volts. Once it reaches 0.7 volts, it is now considered to be forward bias. Okay? If the input is 0.8 volts, is it still forward bias? Yes, but let us analyze doon sa ating circuit. Nung 0 volts yung input natin, hindi pa rin siya forward bias. Kasi nga, hindi pa naabot yung 0.7 volt. Kahit na positive ang anode with respect to the cathode. But the question is, what will be the output voltage if the input is still at 0 volts? So maglalagay tayo dito ng additional na table to write down our output voltage VO. Okay? Since reverse bias siya, it's considered to be open circuit, right? Kung naka-reverse bias siya at naka-open circuit, walang kuryente. Walang kuryente, walang voltahe. So what will be the output if the input is 0 volts? The output is still equal to 0 volts. Kasi nga walang daang kuryente. Naka-reverse bias pa yung ating diode. How about 0.1? Nung nag-increase na sa 0.1 yung ating input, it's still reverse bias. Kung reverse bias, edi 0 volts pa rin dahil walang daanan si kuryente. The same with 0.2. Okay? So on and so forth until ma-reach natin 0.7. The question is, what will be the output voltage? Okay, balik tayo dun sa ating diagram. Ang input mo ay 0.7. Ayan, 0.7 volts. Anong threshold ni silicon? 0.7 volts. Via voltage divider theorem. Hindi ko alam kung na-discuss na sa inyo sa circuits. Via voltage divider theorem. Yung input mo ay mahati sa pagitan ni silicon at ni R sub L or ni load. So the question is, ano kaya ang matitirang voltahe kay load? Alam natin, naka-forward bias si silicon. May dadaanan na kuryente. No? Pero, as you see here, yung voltahe natin, napunta lahat kay silicon. Kasi ang input mo ay 0.7 pa lang. Okay? So 0.7, 0.7, ano magiging voltahe ko dito? It is 0. Kahit na naka-forward bias siya. Bakit? Kasi nagsisimula pa lang siyang mag-conduct. Okay? Nagsisimula pala siyang mag-conduct. So the output, if the input is 0.7, it's still equal to 0 volts. Okay, naging 0.8 yung input natin. No? Kasi nga, di ba, mag-range siya from 0 to 10. So, ang input natin is naging 0.8 na. So, sulatan natin dito ng 0.8 volts. Okay. Ang silicon, once it is turned on or once it is forward biased, it will retain its threshold voltage. Okay, ulitin ko. Ang silicon or any diode na naka-forward bias will retain its threshold voltage. So ang threshold voltage niya is 0.7 volts. Kahit na ang input mo ay 0.8 volts. So what should be your output? So ang output natin dito is now equal to 0.1 volts. Bakit? Kasi nga voltage divider theorem. Yung input mo, mahati sa pagitan ng silicon at ng load. 0.7 plus 0.1 is equal to 0.8. So isulat natin doon sa table natin. So we have 0.1 volts. Okay, let's say naging 0.9 volts. Anong kondisyon ng diode natin? Forward bias pa rin yan. Okay? Kasi na-maintain niya yung 0.7. What is the output? The output is 0.2 volts. Bakit? So balik tayo dito. 0.9 to, yung input natin. And then i-maintain pa rin ni silicon yung kanyang 0.7 volts. So that 0.7 volts, ito 0.2 volts na siya. Para pag inad natin siya, 0.7 plus 0.2 is equal to 0.9 volts. So ganun lang yung nangyari. No? Once na forward bias si silicon diode, it will maintain 0.7 and then mag-i-increase na mag-i-increase yung voltahe natin sa output. Depende dun sa ating. Okay? So let's say it has reached 10 volts. So mag-jump tayo ng a few values. So let's say 10 volts. What is the condition of your diode? Is it forward or is it reverse biased? So let's say 10 volts na siya dito, yung pinaka-peak, yung pinaka-mataas. No? Is it still considered to be forward biased? Yes. Kasi nalagpasan mo yung 0.7 volts na kinakailangan ng silicon para siya ay mag-forward biased. Okay? So this is 10 volts. But the question is, what is your output voltage? So the output voltage now is equal to 9.3 volts. So 0.7 plus 9.3 volts is equal to 10 volts. Nagkaroon ka pa rin ng voltage divider. Okay? So next, we have to determine what we call the transition voltage. Ano ba yung tinatawag na transition voltage na yun or V-trans? V-trans is the transition voltage. What do we mean by transition? Ibig sabihin nagpalit, di ba? May transition, merong pagpapalit. Ibig sabihin yan, ano ang nagpa-forward bias doon sa ating diode? Anong value ng voltahe? From reverse bias, papuntang forward bias, anong voltahe ng input yun? Ang voltahe ng input na yon is 0.7 volts. So this is considered to be your transition voltage, the 0.7 volts na input. Kasi from reverse bias, naging forward bias yung ating diode. Okay. Next. So, ano yung magiging output natin dito? Di ba dun sa ideal diode natin, kung ano yung pumasok, yun yung lalabas. Bakit? Kasi sa ideal diode, it's equivalent to a wire or a short circuit. So, kung ano yung pumasok, siya rin lumalabas. Dito, sa silicon diode, ano nangyari? Bumabawas pa yung threshold voltage ng silicon. So, what will be the highest the highest value of your output? Magkakaroon ka lang ng highest value ng output for the highest value of the input. Ano bang highest value ng input natin? In this example, 10 volts. So anong output natin? 9.3. Kasi bumawas yung 0.7 nung silicon. Okay? So this is the highest value, 9.3 volts. Mamaya ipa-plot natin yung input over versus the output waveform para makita natin yung difference niya with the ideal diode. Okay? So punta naman tayo sa negative half cycle. So negative half cycle, kung mapapansin natin dito, it's the same thing doon sa ating ideal diode. So we have, this is your half-wave rectifier. So we have negative 10 volts, negative yung taas, positive yung baba. So all throughout the negative half cycle, negative ang anode at positive ang cathode. Kung negative ang anode at positive ang cathode mo, it's considered to be an open circuit all throughout the negative half cycle. So ito ang kanyang equivalent circuit. Okay? So kahit napasukan mo pa siya ng pasukan ng negative 10 volts, yung pinakamalaki sa negative half cycle, naka-reverse bias pa rin siya. So what is the output? The output here, walang daanan ng kuryente, so walang kuryenteng pupunta kay load. So the output is equal to 0 volts during the negative half cycle. Okay? So let us now plot the input versus the output. So para makita natin yung difference niya. So siguro ang gawin ko, input, ideal diode, and then yung practical diode, yung silicon diode na to, para makita niyo yung mga difference nila. Okay, so let me just draw the input. Ito yung input natin, no? We have a sine wave, V sub I of t, and this is t. This is your sine wave, so positive half cycle, negative half cycle. So i-project natin pababa. Ganito yung magiging output natin kung ideal, no? So V sub O of t. Yan. Lagyan natin ng broken lines. Assume na lang na na perfect yung pagkakadrawing ko kasi hindi ko talaga ma-perfect yung drawing ko dito sa writing pad. So we have positive half cycle, negative half cycle, peak voltage is 10 volts, negative 10 naman para sa negative half cycle. Okay. Sa ideal diode, ganito ang magiging itsura ng output. So for the positive half cycle, may output ka all throughout the positive half cycle. Kunwari mo kung sine wave na lang ha. Anong pinakamataas? 10 volts peak. Okay. Kung ano yung pumasok, yun yung lumabas. Sa negative half cycle, all throughout, it's equal to 0. Bakit? Kasi naka-reverse bias yung ating diode. Therefore, it's open circuit, walang daanan ng kuryente. Pag dumating ulit yung ating second positive half cycle, what should be the output? It will still be your input. Kung ano pinasok mo, yun yung lalabas. So 10 volts peak pa rin yan. So on and so forth. Pero, what if ang ginamit natin ay silicon diode? So kung silicon diode siya, babawas ng 0.7. So ang pinakamataas dito should be 9.3 volts. Pero tingnan natin, no? Pero hindi ganun kadali yun na matic 9.3 yung pinakamataas. Kukondak agad siya sa 0, hindi. Sa 0 volts, mapansin nyo, based sa ating table, ang output natin is still 0. Sa 0.1 volts, output natin is still 0. Sa 0.7 volts, output natin is 0 pa rin. Nagkaroon lang tayo ng output na 0.1 nung ang input natin ay naging 0.8. So ganito yung mangyayari. Let's say this is 0. So ang output mo dito is still 0. 0.1, 0 pa rin. So on and so forth. Until 0.7. Let's say this is 0.7. Sa 0.7, project natin pababa. Ano kayang output natin sa 0.7? 0 pa rin, di ba? So 0 pa rin yan. Flat pa rin. Pagdating ng 0.8, doon pa lang siya mag-i-increase. Okay. Until ma-reach niya ang alin? 9.3 volts. Until bababa pa siya dito. Okay? Yan. So, kumpara natin yung output ng ideal diode tsaka ng practical diode. Yung ideal diode nagko-conduct agad sa 0 volts. So, meron na agad siyang output. While in reality, yung practical diode natin, which in this case yung silicon, nagkakaroon lang ng output kapag 0.8 na yung input natin. So, from 0 hanggang 0.7, 0 yung output natin. So may onting 0 siya. Okay? Unlike ito, nagsimula agad sa 0, meron na agad value yung voltahe natin. So that is the difference between the ideal and the practical diode. Sometimes it's easier to use the ideal diode model kasi on or off lang, di ba? Meron or wala lang. Short circuit or open circuit lang. Ito hindi. Kung consider mo pa yung 0.7 na bawas. Kaya ang highest lang niya is 9.3 volts kapag ang input mo is 10 volts. Okay, how about the negative half cycle? Ganun din. No? So, mangyari dito, 0 pa rin all throughout. Kasi nga, open circuit siya considered. Pagdating ng kasunod na positive half cycle, hindi agad siya magko-conduct. May panahon na 0 pa rin siya. Diba? Pag na-reach yung 0.8, saka lang siya magko-conduct. So on and so forth. So ang pinakamataas again is 9.3 volts peak. So yun ang difference nila. Okay? In reality, ganito talaga yung nangyari. Babawasan tayo ng 0.7 volts dahil doon sa voltage drop na tinatawag. When we say voltage drop, ano pagkakaintindi mo sa voltage drop? In terms of voltage drop. Voltage drop is just a drop in potential. Or this is your induced voltage. Huwag kayo malilito dyan. Okay lang yan. Walang problema doon sa terminology na yan. Let's say, ito. Yan. So, dito sa ating diode, it has a voltage drop of 0.7 volts. Okay? Ang load natin, it has a voltage drop of 9.3 volts. Bakit? From positive, naging negative. From positive, naging negative. So, voltage drop yung tawag. Or, kung negative yan, negative man, negative and positive sa baba, voltage drop pa rin yun kasi considered as induced voltage siya. Okay, so terminology yun sa electrical circuits natin. Okay? So next. So this is the output of a half-wave rectifier. So this is called a half-wave rectified waveform. Okay? So all we have to do here is to determine kung maganda ba yung isang half-wave rectifier compared sa isang full-wave rectifier. Okay? So in order for us to do that is we will perform integral calculus. So integral na yon, kailangan natin makuha yung average DC voltage. Ang average DC voltage is defined by this equation. So VDC is equal to, kukunin muna natin yung average niya, and then meron tayong integral. When we say average, ano ba ang ibig sabihin ng average? Di ba average, ina-add natin lahat ng number divided by the total. Okay. So, ang ginagawa natin dito, when we perform integral, we're like adding. Adding the entire value of the waveform in concern. Kagaya nito. Halimbawa, this is 0 radians. This is 5 over 2 radians. This is pi radians. This is 3/2 pi radians. And this is 2 pi radians. In short, kung ito ay naka-degrees, this is 0 degrees, this is 90 degrees, this is 180, this is 270, this is 360 degrees. Okay. But in our calculation, we will use radians. Okay. So, ang range natin is from 0 to 2 pi radians. Okay? So range is from 0 pi radians to 2 pi radians. Yun yung total ng x-axis natin. Okay? Kaya para makuha natin average, we will divide the entire thing by 2 pi radians. Kasi kung susukatin mo yung 0 to 2 pi, gaano siya kahaba? 2 pi siya, di ba? Kasi 2 pi minus 0 is 2 pi. So 2 pi yung range natin for the x-axis. Okay? So for the entire 2 pi na coverage niya, i-add natin lahat ng values. No? In order for us to add the values under the curve, di ba? Area under the curve, naalala niyo sa integral. Area under the curve, we get the integral calculus of that. The integral rather. We get the integral of that. Okay. So first is determine muna natin yung equation ng ating waveform. So ano kayang equation ng waveform ko dito? Focus on this one, this one. Okay? Gamitin natin yung sa output ng ideal diode. Kasi kapag gagamitin natin practical diode, magma-minus pa tayo ng 0.7. But anyway, makukuha mo rin naman yung same answer no, kapag gagamitin natin tong ideal diode. Okay. Ano kayang equation ko dito? Di ba this is a sine wave? Or cosine wave kaya yan? Ano kayang difference ng cosine wave tsaka ng sine wave? So pakikita ko muna sa inyo ang difference ng sine wave tsaka ng cosine wave. So I will use Scilab to plot a 1 kilohertz waveform using sine and cosine function. Ito. So I have here, i-define ko muna yung time. Ano ang period ng 1 kilohertz na signal? 1 millisecond. Kasi 1 kilohertz, 1 over 1 kilohertz is equal to 1 millisecond. So I'll start with 0. Ang increments ko ay, let's say, 5 0. And then ang ending value ko is 0.001. Yung 0.001, it represents 1 milliseconds. 1 millisecond rather. So enter. Anyway, nagawa niyo naman to dati. No? May assignment pa kayo dito. Diba? Kung ginawa niyo talaga. Okay, next. I will define now, let's say, VT sine. Okay. Yung variable na yan, ginagamit ko to assign to a sine wave. Let's say, ang amplitude ko is 10 times sine of 2 times percent pi, 2 pi ft, di ba? Times, ano yung frequency natin? 1,000 hertz or 1 kilohertz times t. Okay? And then, assuming phi or phase is 0, enter. So, I will now create my variable for cosine wave, Vt cos. Pwede kayong gumamit ng ibang variable kung gusto nyo, walang problema dyan. 10 times cosine of 2 times percent pi times ano yung frequency natin? 1,000 times t. Okay, enter. So I have now defined my waveform para sa sine wave tsaka para sa cosine wave para makita ninyo. Okay. So walang problema sa time kasi parehong time yung gagamitin ko dahil pareho namang 1 kilohertz yung frequency. Ang pagkakaiba lang nila yung isa sine wave at yung isa ay cosine wave. Ano kayang itsura nila? No? So I will now plot XY, di ba? Ang command natin is XY. Ang magsisilbing x-axis natin is time. Ang y-axis natin is yung voltage. So let's say VT sine. Okay? So ito ang itsura ng sine wave. So pag nagsimula tayo sa 0, 0 ang value niya. Kailan siya magiging maximum? Magiging maximum siya dito if this is equal to 90 degrees or pi over 2 radians. Okay. Pa-plot ko ngayon si cosine. Gagawin ko siyang pula para makita natin yung difference. So, plot t, which is the x-axis. Ang y-axis ko naman ngayon is cosine wave. And then, gagawin ko siyang pula. So, comma, single quote, red, yung word na red, and then close parenthesis. So, yung pula na wave dito na lalabas is a cosine wave. Ito yung tsura niya. Yan. So I hope nakikita. So ito yung blue na wave, this represents your sine wave. Yung pula, this is cosine. So ang cosine, nagma-maximum siya if it is equal to 0 pi radians. Okay? So yan ang difference ng sine wave tsaka ng cosine wave. They are out of phase by 90 degrees or they are out of phase by pi over 2 radians. Yun ang separation nila. Di ba sa trigonometry, meron tayo niyan, sine theta is equal to cosine 90 minus theta. So cosine and sine are separated by 90 degrees or pi over 2 radians. So ibig sabihin, ang equation ng ating waveform for the output during the positive half cycle, anong equation nito? Pag 0 radian, 0. Alam natin na sine wave yon. Okay? Hindi siya cosine wave kasi ang cosine wave, nagma-maximum siya kapag 0. Ito, 0, pero 0 pa rin. So ang equation nito, from 0 to 180 degrees, this is a sine wave. Okay? How about this one? From 180 to 360, ano kayang equation nito? May nakikita ba kayong sine wave dyan? Wala. May nakikita ba kayong linya? Yes, diretsong 0. Therefore, ang equation niyan ay equal to 0. So let us write the equation between 0 to 180 degrees. So this is 0 degrees to 180 degrees or masanay na tayo in terms of radians. So from 0 pi radians hanggang pi radians, yan yung range natin. From this point up to this point, that's from 0 radians to pi radians or 0 degrees to 180 degrees. Ano daw ang equation ng ating sine wave? So that's equal to V of t is equal to, let's represent the magnitude as V of m. times sine 2 pi ft plus phi. Okay? But to simplify our analogy, we can represent this term in terms of theta para mas madali. Anyway, you will still get the same answer. Okay? So we have V of t is equal to Vm sine theta. Plain and simple. Okay? So this is the equation of the waveform, of the output waveform rather, the output waveform between 0 pi radians and pi radians. So kung gagawin daw nating equation form, yung output natin from 0 to pi radians, ito daw siya. Okay? Next, from pi radians to 2 pi radians. From pi radians to 2 pi radians. Ano daw ang equation natin? So, wala naman kayo nakikitang output, di ba? From pi radians to 2 pi radians. Dito, this is pi radians or 180 degrees. This is 2 pi radians or 360 degrees. Walang output. So, anong value ng waveform mo? 0. So, we will write here V of t is equal to 0 volts. Okay? So these are our working equations para makuha natin yung DC value. So this is how we set up the equation for the DC value. Ilang DC daw ba makukuha natin dyan? Okay. So VDC, this is also known as the average voltage. Average voltage or DC voltage is the same. Okay? This is equal to, paano natin kukunin yung average? Dinidivide natin sa total, di ba? Ang total natin is 0 to 2 pi. So 2 pi minus 0 is 2 pi. That's why i-divide natin yung whole equation by 2 pi. This is how we get the average. Okay, next. How do we get the total? In order for us to get the total, we must get the integral. So hihiwalay natin ang dalawang integral. Kasi isa for the positive half cycle, which is from 0 to pi radians. Isa sa negative half cycle from pi to 2 pi radians. So 0 pi radians hanggang pi radians. Ano daw ang equation? Anong mathematical equation ng ating waveform between 0 and pi radians? That's equal to Vm sine theta. Pero may integral ka, so lalagyan mo siya ng d theta. Okay. Next. From pi radians to 2 pi radians, ano daw ang equation ng ating output? May nakita ka bang output? Wala, 0. So maglalagay tayo ng 0, d theta. So this is our working equation to determine the DC value ng ating half-wave rectified signal. Okay. So, sige. Paano natin kukunin yung integral niyan? Ito madali lang kasi magsisiro tong isa eh. So tanggalin na natin yan. Okay, dito tayo ngayon nakafocus. Okay, so let's separate this one first. So integral from 0 pi radians, and then mamaya multiply na lang natin sa 1 over 2 pi. 2 pi radians Vm sine theta d theta. So ano ginagawa natin kapag merong constant sa integral? Matik, nilalabas natin ang integrand, di ba? So, constant si V sub m. So, ilalabas natin siya ngayon. Equals V sub m from 0 pi radians to pi radians. Matitira na lang sa loob si sine theta d theta. Ano ang integral ng sine theta d theta? Ang integral ng sine theta d theta is negative cosine theta plus c. Okay? So, ilagay ko dito sa side note natin. The integral of sine x dx is equal to negative cosine x plus c. Huwag kayo malilito dyan kasi ang derivative naman ng sine is positive cosine. Pero ang integral ng sin x dx ay negative cosine plus c. Assuming zero initial conditions, so eliminate natin yung c. So ang kailangan na lang natin is negative cosine x. Ano ang nagsisilbing x dito? Yung theta. So this is now equal to v sub m times times negative cosine theta with limits from 0 pi radians to 2 pi to pi radians. Okay. Ano ginagawa natin sa proper integral? Nire-replace natin yung variable ng upper limit and then minus natin yung lower limit. Ano yung upper limit natin? Pi radians. Ano yung lower limit natin? 0 pi radians. Okay? So, lagay natin dito, that's equal to v sub m times negative cosine of what? Upper limit is pi radians. So, kahit lagay na lang natin yung pi, kahit hindi na yung radians, para hindi masyadong marami nakasulat. Actually, pwede natin ilabas yung negative na dito para hindi na tayo malito. Yung negative cosine na yun. Negative Vm na yun. Okay. Times cosine minus lower limit. Ano yung lower limit natin? 0 pi radians. So that's cosine of 0. Make sure yung calculators natin naka-radians. So, natin kung merong scientific calculator dito sa dali. Okay. So ito. Hindi ko alam kung paano i-radians itong sa sa Windows pero I think naka-degrees eh. Okay. So pipindutin ko dito sa hindi ko alam kung paano gawin radians. Degrees na nga lang. Ito. Ayun, yun, radians. Okay. So, cosine of pi. So, pipindutin mo muna yung pi and then cosine. Cosine. So, cosine of pi is equal to negative 1. Susulat natin dito. Cosine of pi. Make sure naka-radians ha. Cosine of pi is equal to negative 1. Minus cosine of 0. Equal to 1 yan eh. Kahit na naka-radians yan. Pero papakita ko pa rin sa inyo. Clear? 0, then cosine is equal to 1. Okay? So minus positive 1. So cosine pi is negative 1. Cosine 0 is 1. Negative 1 minus 1. Ang dami nagkakamali dito. Mababalikin ko kayo ng elementary kapag sagot nyo dito 0. Negative 1 minus 1 is not 0. Negative 1 minus 1 is equal to negative 2. So this is equal to negative v sub m times negative 2. So this is equal to positive 2 Vm. Pero hindi pa dyan nagtatapos kasi hinugot lang natin siya dito, di ba? So isasalpak natin doon, pabalik sa equation na yun. Balik natin siya doon. So this is equal to 1 over 2 pi. Integral nito, ito, is equal to 2 times Vm. Wala na tayong pakialam dito sa second term kasi magsi-zero na siya eh. Okay? So pwede natin i-cancel yung 2. This is Vm over pi. Okay? So ibig sabihin yan, that is your DC. So explain ko maigi anong importance ng Vm over pi na yan. Tatandaan nyo ang DC or average value ng isang half-wave rectified signal is equal to the peak voltage V sub m divided by pi. Okay? Vm over pi ang kanyang DC value. So balik tayo dun sa kaninang waveform. Ito yung output ng half-wave rectified, di ba? Meron, wala. Meron, wala. So this is a pulsating DC na half-wave rectified. Ano yung ating ano yung peak voltage natin kanina? 10 volts. Diba? 10 volts peak. Ano ang peak to peak ng input natin? Okay. the peak-to-peak of the input is equal to 20 volts peak-to-peak. Supposed to be 20 volts ang na-utilize natin. No? Pero the thing is, how much DC are we getting out of it? No? Anong value ng DC ang nakukuha natin dun sa ating output? Kasi yun ang function nito eh. Para makakuha tayo ng DC galing sa AC. Okay? So, in order for us to answer that question, we must use this formula. VDC is equal to V sub M over pi, which is yung sinod natin kanina. Okay? So, that is equal to 10 divided by pi. 10 volts peak yan, ha? Equals. So, i-calculator natin dito. Pakita natin dito. Calculator. That's 10 divided by pi is equal to 3. Round off natin sa 2 decimal places. 3.18. Usually, sa klase ko, 2 decimal places ang pinaparound off ko unless otherwise specified. So, 3.18 volts. Anong ibig sabihin yan? Anong ibig sabihin yan? Every half cycle, ang pumapasok ay 10 volts. Ang pinakamataas na pwedeng pumasok ay 10 volts. Right? Dito sa example natin. Pero nung ginawa mo siyang DC, ang nakuha mo na lang ay 3.18 volts. Tignan nyo from 10 volts, ang nakuha mo lang 3.18 volts. So it's very less efficient. Half-wave rectifiers are less efficient in terms of power supply. So hindi natin gaanong ginagamit or hindi natin ginagamit talaga ang half-wave rectifier bilang isang power or part ng isang power supply circuit. Bakit? Kasi nga, tignan nyo, 10 volts, ang nakuha mo lang 3.18 volts na DC. Okay? So that is how we calculate the DC voltage or the average voltage of a half-wave rectified signal. Okay? So siguro dito ko muna tatapusin para hindi masyadong maghalo-halo sa inyo. Again, ipiprint out ko tong lecture natin, isasend ko dun sa ating DC. Tapusin ko na muna ngayon ang ating lecture. And then we'll continue next time with center tap naman. Center tap full wave rectifier. Okay, so attendance. Attendance muna bago tayo mag-dismiss. Kasi pag tinuloy ko to ng center tap, baka maguluhan na kayo, maghalo-halo na lahat. So attendance muna tayo. Arsenal, Samsung, Bakujo, Visa. 1, 2, 3, 4, 7. Meron natin answer. Arsenal, bakit? So yan na yung mga 1, 2, 3, 4, 5, 6, 7. Ayan. Attendance. Okay. So kung meron kayo katanungan, pwede nyo na ma-post dun sa ating group chat. Okay. So just see you next week. Okay, bye.